Okay, so now we're going to be discussing about the second definition, homogeneous differential equation. Now, the first definition is in the event that we have some kind of function containing f of y prime, so on and so forth, y to the n power, that this is equal to 0. In essence, that there is no f of x. So that is the first definition of homogeneous. Now, the second definition is given by the following, that all powers of each term are the same. Now, this is characterized by the following relation. F of tx ty is equal to t to the n f of xy. So we can factor out a common power and show that it is in fact satisfying this condition. Now, suppose that we're given some kind of relation m dx plus n dy equal to 0. Now, if we recall from last time, this one is just a special case, or a case of an exact differential equation. But under the condition that all powers of each term are the same, we can actually apply another method. So first, m is dependent on x and y. But I suppose that I can factor out all x's to give me 1 and u. Now u is equal to y over x. And if we do a little bit of manipulation, y is equal to ux. Or we can do n, which is also dependent on x and y, equal to y n v 1, where v is equal to x over y, or such y is equal to, or such x is equal to vy. Either method is the same for both of us. However, I'm going to use this one mainly because this is an easier, clear-cut way for me to show you that usually we want to substitute in y rather than x, because x is usually denoted as our input, and if we just substituted x, then it kind of defeats the purpose of kind of keeping it consistent that y is, in fact, the dependent variable. So first, if we're given some kind of m of xy, and we can factor out x, we get 1 and u. Now, this leads us to the procedure. 1, we have to check, are all powers of each term the same? So all powers the same. If yes, then we can actually apply second definition homogeneous. First, we keep two terms. U is equal to y over x. Or rather, I should say y is equal to ux. If we take the derivative, we get dy equals to u dx plus x dy. Or sorry, x du. Now, we keep the following in our back pocket because we're going to use it for later. We have u equals y over x as our substitution for going back to y. Now, in this situation, that's it. We just then have to solve some function f dependent on u. Du equals to f of x dx. that's the form that we should get. And that we can then substitute as u equals f of x plus c. So this is our fourth step, just to kind of solve for everything in terms of this new variable u. Now, because we have u, we have the ability to substitute everything that contains u with y over x. So as such, we have y over x equals to f of x plus c. Now note, this is a bit of a misleading form. This doesn't necessarily mean that the form is able to be simplified like this, as discussed before with separable differential equations. This one we can't solve for until we are given an example to do. And as such, that is what we will do when we're finished with this video. So just to kind of recap, the second definition, homogeneous, means that all powers are the same. All powers of each term are the same. As such, we can then use the following substitution: ux and then u dx plus x du. Now, why do we want to do that? Well, first, the goal is to turn from a second definition to a separable. That's our reason why. And in the next video, we'll demonstrate how to apply the methods as discussed here. Okay, thank you.